And on this platform, there's a spindle in the middle, and I've attached a spring to that spindle. And at the end of that spring is a box. And for the moment, let's just say the whole system is at rest. All good? All right. Let's also establish that there's no friction between the box and any part of the platform, but some guide rails have been placed on the platform so that the box can only move in a radial direction. You guys understand what a radial direction is signifying to you? Good. If we were to spin the system up, would you agree that the spring is likely to stretch? That seem like not an unreasonable thing? All right. So let's do that. Let's say that we apply a torque to the system and we spin the system up so that we get to some constant angular speed. And by doing that, the spring, which was length d, now stretches an additional amount. Box is mass m, spring constant value k. Do you have the necessary skills, without looking at your notes, to get an expression for x in terms of the other variables? Could you try? Let's consider that in this problem, if you were thinking about work and energy, because there's a spring, and we've said before that springs suggest energy sometimes, that energy has to be delivered to the block somehow. And in this case, I don't see a delivery of energy to the block. The motion of the block is not directly attributed to something the spring is giving to the block, right? There's not energy in the spring that's being delivered to the block. The spring is stretching, sure. Is the spring applying a force to the block? Yes. Is the spring doing work on the block? Like for there to be work done, which is how you get energy to go from one place to another, the force of the spring has to cause a change in displacement of the block. And just consider what the block is doing. The block is experiencing a force in this direction from the spring. Agreed? Is that force causing a change in the motion of the block? Meaning the block is going this way, right? That's the direction of the block at this instant. By definition, work equals the integral of f dot dx, which I saw in a couple of papers. And I kind of chuckled to myself, because you forget what this is about. Work is only done if the force causes a change in displacement. I don't think that the spring is causing a change in displacement. Moreover, the dot product is the angle between the force and the displacement. So if we replace this with cosine of that angle, what is the angle between the force and the displacement? 90 degrees. This force from the spring does no work on the box. The force from the spring, what does it do to the box? It what? It keeps in circular motion. It changes the direction of the box. What do we call that? What kind of acceleration doesn't change speed, but only changes direction? Centripetal. That's right. This problem is a centripetal motion problem. What's the only way you can cause a centripetal acceleration? You need to know this. Will balanced forces cause a centripetal acceleration? Or unbalanced forces? This is a Newton's second law problem. Now, in that little 4-column thing, we probably put circular motion as like an ancillary topic. It's a form of two-dimensional motion, but it's an acceleration, which means it's a force problem. Force problems are good at giving you acceleration or individual forces. This is a force problem. Start it there. As this is not the only one I want to see today, and because this is a question you've seen before, we really shouldn't work that hard on this. If omega is constant, the walls themselves don't necessarily apply a force to the box. They would have to apply a force to the box if omega wasn't constant, because they would be changing the tangential speed of the box. They keep it in the column though. Now, you should have started with net force equals ma and put the little c there. What force is acting on the box? We're looking top down. Can you tell me what arrows I should draw here? What direction? All right. Force from spring. Anything else acting on the box? I mean, we have weight and normal, but wouldn't that be balanced and be zero? Any force this way? Why does the spring stretch then if there's no force that way? This is an important question, and one if I ask you to justify what's pulling out the spring, could you give me a justification? The spring clearly stretched. You all said that you would believe that if you spun this up, the spring would stretch. But there's no force causing it to stretch. Then what's causing it to stretch? I'll accept it, but it's probably the wrong word to use there. The box is inertia. The box wants to travel in a straight line, this straight line, right? The spring has to pull on the box in order for it to change that direction. The more force that's necessary to change the box's direction, the more the spring will have to stretch so that its force increases to be enough to cause it to change the direction. What's the force from a spring? Yeah, it's minus kx, not kx squared. Although I saw a lot of squareds out there. And remember, you have an equation sheet. It's going to tell you force as different from energy. The negative sign is about direction. The spring is stretched to the left, so the force is to the right. And the acceleration is also to the right. So if I'm going to use this here, I'm just going to put kx. And of course, I do have something I can put in there for omega squared. But I can't have r in my answer, can I? What does r stand for? What's that?
The radius that it travels in.
The radius of curvature is the word I'd like you to use. So m omega squared. What is the radius of curvature? Now, is this x the same as this x? What does the x over here stand for? So it's how much the string is stretched from equilibrium. In what way is this one different then? You're the ones who said they were not the same. I believe they are the same. If D represented the relaxed position of the spring, then X has to be how much the spring has been stretched from its equilibrium position. I think they're the same X. Wow, this is a tough one. You guys are a tough crowd today. Can you solve this for X now? That's just algebra, right? I'm not particularly interested in the answer, but does the answer conform to something that you believe to be true? For example, if we increase omega, does your equation show that X increases? You should check. You should solve this for X and see if it's true. I'll give you so there's not a whole lot, it's just algebra. Does it conform? If omega gets bigger, does X get bigger? It seems to me that it does, right? Obviously, omega's in the numerator, so if omega gets bigger, we automatically see that the top is going to get bigger. In the bottom, it's k minus m omega squared. So at the same time that we're making the top bigger, we're making the bottom smaller. That seems like that makes X bigger under both circumstances. Looks like there's some limits though too, doesn't it? Some potential limits in there. The possibility of a 0 exists in the denominator where X could be infinite. That seems like a weird state, like something doesn't seem right there. But you should look into it a little bit. All right. Not particularly hard. I wanted to use this as a warm-up question, but then when I saw how difficult everybody thought this problem was, I was very disappointed because the real problem I want to talk about isn't this one. This one's a walk in the park, should be. And yeah, there could be more parts to this. There could be other things. Circular motion problems are generally going to start off as a force problem, or are going to have a force problem in them. It's an unbalanced force that causes an acceleration, and the acceleration is special. It works velocity, and sure, that's because it's traveling in a circular path. It's still about force and acceleration. So these problems are going to be net force. There could be other questions. Like I could ask you, what is the angular momentum of the box? You would have two ways to possibly find it. That should be pretty straightforward. You should be able to do that. These are side problems. We could even say, how much kinetic energy does the box have? Sure, why not? Right? That's not a particularly challenging question either. Those are side projects, plug and chug kind of things. But you would have to know that, oh, do I treat this as do I treat it like a point mass traveling in a circular path, or do I treat it as an object that has a moment of inertia? And you should know too, because we've just recently studied it, that it doesn't matter, that you will get the same answer whether you treat it as a point mass or you treat it as something that has a moment of inertia. You should prove it to yourself why that's true. But I want to talk to you about the real problem that was supposed to be today, the one that's related to yesterday's conversation. And I was trying to kind of finish out yesterday's conversation, so you can understand how shocked I am that I can't. So let's talk about the real question. And this is a problem that you've seen before as well. It's a problem in which there's a ring that's set up like on a table, and there is a ramp a box is placed on the top of the ramp, and the box on the ramp is height h. There's no friction on the ramp. The box has mass m, and it slides down the ramp and into this ring. From the top, the ramp basically extends right here on the edge, and the box, although started, say, here, slides down the ramp and eventually makes it to the surface. Sound familiar? Remember this problem? The first question was a conservation of energy question, which was to find the initial velocity of the box when it makes it to the ring. That one should be cake and shouldn't be a problem, but I'm nervous for you all. So take 30 seconds and let me pick on one of you to tell me what the initial velocity of the box will be when it makes it to the bottom of the ramp. You may assume the ramp is frictionless. We have one right answer today in this class. Woohoo! All right, good. So the rest of the problem changes dramatically. The first part was just that. Can you find an expression for the initial velocity? From this point forward, you're allowed to use v naught as your initial velocity. The floor of this particular arrangement has no friction, but the wall does. The wall has a coefficient of friction of mu k. Set up, but do not solve, a differential equation that could be used to find the velocity of the block as a function of time after it goes down the ramp. I'm talking about these kinds of problems, and this is the one I want to talk about. I'll say it again. Set up, but do not solve, a differential equation that could be used to determine the velocity of the block as a function of time after it has slidden down the ramp. There's not a whole lot here. We put it together so you have at least a place to start. There's not a whole lot here, but again, net force in the x direction, net force in the y direction, and then we needed to find a way to bring friction and normal force together. it's still your series of steps for forces. We really didn't go outside of that at all.